Hello. So today we'll be going over what actually is a matrix. So you probably know that a matrix is just a series of numbers arranged into columns and rows. But what do these actually mean? What do these numbers actually represent? I think the best way to think about this is by using linear algebra. So if we just take a random matrix here and act it on the vector 1 in the x direction, then let's see what we get. So first off, we need to work out what we actually produce. So as the matrix has dimensions 2 by 2 and the vector has dimensions 2 by 1, we have to match these two numbers in order for matrix multiplication to work, as you probably know. And then we're left with the dimensions of the resulting vector or matrix being these two numbers here. So let's actually do this matrix multiplication. So we take the first row of the matrix and we times this by that, and add them together. So we get 0 on the top here of our resulting vector. Then we do the same but for the next row in the matrix, and we get 1. So we get 0, 1, which you may have noticed is actually the first column of our matrix, which are actually acting on the vector. So let's do the same but for the vector of 1 in the y direction. And churning through the maths, we get that the result is the second column of the matrix. So this is an interesting result, but let's dig in further. So let's do the vector of 2 in the x direction. Going through the maths again, we just get double of what you got for the vector of 1 in the x direction. And again, for the vector 1, 1, we just get the sum of our results for the vector 1 in the x direction added on to the vector that we got when we did the matrix times the vector 1 in the y direction. I think from this we can see that a matrix seems to have the same effect on any vector. So you just get your vector and you split it into linearly independent components. We usually just do x and y, they're perpendicular to each other, so they're linearly independent. So you can't make y out of any multiple of x, and vice versa. So our matrix acts on each of these, with its effect being described by each of the columns. So the first column being for x, and the second column being for y. And if it was 3D, we'd have a third column for z, and so on. And then you times by any scale factor, as we saw. For example, if you're going 2 in the x and 1 in the y, you times the first column by 2 and the second column by y, and then you'd add these results together to get your overall vector result. In the example we used, the matrix actually represents anti-clockwise rotation of 90 degrees. We can see this by plotting the start and end result for the 1, 1 vector, as shown here. You can see this is 90 degrees. So we can clearly see that it rotates the x vector by 90 degrees. It rotates the y vector by 90 degrees, and it just rotates any arbitrary vector by 90 degrees. As you can write any arbitrary vector as a sum of these two, along with some scale factors. So a matrix is basically just a transformation, is what we call it, with the first column of the matrix only caring about the x input, and the second column of the matrix only caring about the y input. Now if we look within the first column of the matrix, we see that the first row is the x output due to the x input, and the second row is the y output due to the x input. And we can do the same for the y input column to basically make this table, as we can see. So basically you can think of a matrix as like an input-output machine, and we can basically use this to explain why earlier we had to have these two numbers matching in order for matrix multiplication to work. as this number represents the number of inputs being given to this matrix, and this number representing the number of inputs it can receive, so these need to be equal. So, I guess in summary, a matrix can be subdivided into its columns, and these represent the matrix effect on the basis vectors. So the matrix is a transformation. Or even more generally, you could think of a matrix as some kind of input-output machine, and the numbers just represent the relevant outputs for certain inputs into this input-output machine. With this table we made earlier, summarizing the mechanism by which this machine works by.